In this video, we're going to talk about epoxide reactivity. I'm going to start off by talking about some general considerations that we need to think about, and then I'm going to look at two different types of reactions done under nucleophilic conditions and reactions done under acidic conditions. So let's take a look at some of the general considerations that we need to think about. So here I've drawn two different epoxides that we can consider. And the two major things that we need to worry about when we're considering the outcome of a reaction with epoxides are the sterics of our system and the stereoelectronics of our system. So if we think about sterics, we're thinking about what kinds of atoms are getting in the way of our chemistry. So here we have a primary position, and here we have a secondary position. And if we think back to SN2 chemistry, the more substituted the carbon was, the more sterics we have around there, the harder it is to do our chemistry. So this is going to be the better position for us to attack if we're worried just about the sterics. As we start to add more groups around one of these carbons, the steric requirement is higher, and it's harder for that nucleophile to attack those positions. If we think about stereoelectronics, we're not worried about the sterics, but we're worried about the charges that we have or the reactivity that we have at the different positions. Now, in this case, I have a secondary position and a tertiary position. All of these carbon-oxygen bonds are going to have some kind of polarity to them. They're polar covalent bonds. So we're going to have a partial positive charge that's developing on these other carbons. Now, a tertiary center has more alkyl groups that can help stabilize that partial positive charge. So what we end up with is a larger delta positive at those tertiary centers. And that is also going to play a role in deciding which side of this epoxide we're going to be able to attack. So in the next section, we're going to focus in on one type of reaction that we can do with epoxides, and those are reactions that are done under nucleophilic conditions. So in this example, here we have an epoxide that's differentially substituted. We have a secondary center here and a tertiary center here, and we're reacting this with sodium cyanide. And if you remember from our discussion of SN2 and SN1 chemistry, sodium cyanide represents a good nucleophile. We want to treat this as Na plus and Cn minus, but this is a good nucleophile. So if we're reacting an epoxide under nucleophilic conditions, we want to have the sterics dominate. I often think of this as being a true SN2 reaction. So in the case where the steric dominates, we want to go for the side that is sterically more accessible. So in this case, that's going to be the secondary center. And the other thing to consider is this is an SN2 reaction that we're doing, so we're going to get a backside attack on this carbon-oxygen bond. So after this first step, that cyanide should be going away from us because it has to attack the backside of this carbon-oxygen bond. So we see that inversion of configuration at that particular center. So then we can finish up this reaction in the second step by adding something to protonate that oxygen, like water. Notice that the stereochemistry of the other carbon didn't change as we went to the products. We didn't do any chemistry at that position, so we're not going to be changing that center. But the one where we attacked, that's where we get the inversion of configuration. So let's see how this situation changes when we run these reactions under acidic conditions. In this example, we're taking that same epoxide that we just looked at, but now we're going to run this reaction with H2SO4 in methanol. So what happens, the H2SO4 and methanol are going to react to form the acid catalyst that we have, this protonated solvent. And we're going to protonate that epoxide. Now when we protonate that epoxide, that's going to help to activate this epoxide. Once we protonate this, we want to again think about these polar covalent bonds that we have. We already had a partial positive charge on these carbons. By protonating the epoxide, we can actually increase the partial positive charge that we have on these different carbons. Again, the tertiary position is going to stabilize that positive charge better. So we have a larger delta plus at that position. So our nucleophile, in this case, our nucleophile is going to be the solvent, which is methanol. it's going to attack the more hindered tertiary position. And then it's going to open up that epoxide. Now, since we're looking at the delta positive in this case, that's a stereoelectronic effect, not a steric effect. So in this case, the stereoelectronics are going to dominate. However, this is still acting as an SN2 reaction. So when this nucleophile attacks, we still get inversion of configuration at that position. After the nucleophile attacks, we have this protonated ether, so we need to have another solvent molecule come along and pull that off. That's going to give us the product of this reaction. And it's also going to regenerate that acid catalyst that we used. So under acidic conditions, we end up protonating the epoxide, which further activates this tertiary position. This is dominated by where we can stabilize that positive charge. That dictates where our nucleophile comes in. But since this is still an SN2 reaction, we still see inversion of configuration at that position. Again, we don't change this other position because we didn't do any chemistry there. So hopefully you find this information useful as we start to study more reactions that involve epoxides.